Okay, so we're going to do something called stable matching problem or stable marriage problem. Um, so here's a scenario. You've got, let's say you've got n companies. And you've got n, let's say, interns or something. And let's say that each company wants to hire exactly one of these interns. So, I mean, there's different ways I guess a kind of general question is, what's the best way to do it? Which obviously is very not well defined. But I think like a reasonable way you might think to do this is like, I don't know. Like for each intern, you could see, kind of grade them and say from 1 to 10, how good are they at doing that job or something, right? So you could make this like a maximum weight perfect matching problem where, maybe over here you've got interns. And over here you've got companies. And you could do something like, maybe for each intern you kind of judge their skill at doing this job, and maybe this intern, like out of 10, maybe they're like a 5 at that job, but they're really like a 9 at this job, right, out of 10. And then you might want to say, okay, let's take the biggest perfect matching, right? Find the max weight. So that would be what we did last time, which I think is a reasonable approach, right? But in some sense, this is only a reasonable approach if you live in a dictatorship, where like the person who's trying to maximize profit or something is like deciding who gets every single job, right? In reality, that might not work out so well because, I don't know, you could have a situation where it's like, so you could have a situation like this where it's like, okay, so if I'm like the person who's deciding who gets every job, I would just do this, and I'd say, okay, I can get an 11 by doing this. It's not really clear which edge I'm writing this on. Maybe that one's a 9 and that one's a 1. But then like this company over here could be like, I'm really not happy with this selection. I'm just going to offer this guy more money, this candidate more money, and then it's going to like screw everything up, right? So in reality, like, you might want, yeah, that's it's not really how the world works. That somebody picks the matching that's the best for the kind of global situation. Also, you could have this, maybe this person's a 6 at this well, you could have a situation also where an intern is assigned to a job that they're really good at, but they hate it, so then they want to do a different job, right? So the topic we're going to talk about today kind of addresses this issue, that different people might have different preference lists, different companies might have different preferences of interns, and we want to make the matching stable. So we want to avoid the situation where some company actually goes and like gets somebody else, and maybe this intern actually really likes this job, and this job wants that intern. They're gonna just give them the job, right? Okay, so here's the setup. So yeah, let's suppose so each intern has a ranking of all companies. Okay, and let's suppose that every company also has a ranking of all the interns. Now these rankings are arbitrary. Different interns might have the same ranking. They might have opposite rankings. They might have, different rankings. It doesn't really matter. And same with the companies. They could all have different rankings. Or they could all have the same ranking. It's arbitrary. So let's say that a perfect matching, let's say, let's just say a matching is unstable. Let's say a matching M is unstable if there exists actually, maybe let's make this a perfect matching, sorry. Let's say a pair or an edge IC in the matching okay, maybe I should just do this properly. So okay, sorry. So it's unstable if there exists an intern I and a company C such that two things happen. I prefers C over the company it was matched to. So this intern would prefer to work for that company over the one that it was matched to in M. And simultaneously, C would prefer I over the intern that it is matched to. Okay. What this is trying to say is like, this would be a bad thing, right? If you had this situation where this company, I've given them this intern, but they actually want that one. They not necessarily, they like this one better than the one they got, and this intern likes that company better than the one that they've got. Then that's going to be an unstable situation because really, they're just going to fire their intern and take this one, and that one will be happy to leave its company for that one, right? So then it's stable if it's not unstable. So otherwise, M is stable. So I think it's quite unclear whether stable matchings even exist. So maybe two questions. Do stable matchings always exist? And then if they do exist, can you find them in polynomial time? Because to me, it's not hard to imagine that there could be some kind of really bad pathological list of preferences. Maybe where there's no stable matching, no matter what you do, maybe there's always an unstable pair. But yeah. Have any of you heard of this before? Or maybe vaguely somewhere? Yeah, it's a thing that like shows up in, I don't know, like if you watch YouTube videos on math or something, like this is a thing that comes up. But okay, so the answer to both of these things is yes. I guess you could probably guess that. Otherwise, why would I be telling you about this? But yeah, so you can always get a stable matching, and you can do it in polynomial time. It's actually a pretty simple algorithm, which we're gonna talk about next. Any questions about the setup, though? Okay. Okay, maybe I'll write over here. So this is called the Gale-Shapley algorithm. Okay. And it's kind of ridiculously simple. So we're just going to do a bunch of rounds. And in each round, so like in each round, some companies are going to make some job offers, right? And some of those job offers are going to get rejected. Some of them won't get rejected. So in each round, every company that has had all of its offers rejected so far, so that has had every offer rejected so far, makes an offer to the highest person on their preferences that hasn't rejected them already. So it makes an offer. And this happens simultaneously. So all the companies do this. To the highest person on their preference list that hasn't already rejected them. So they're going for the best thing they can get. Obviously, like you could make an offer to someone who already rejected you, but they're probably going to reject you again. So why would you do that? And then so after this, every intern rejects every offer that they've seen, like every offer that they currently have pending. So that they have, except for the best one. If they've already gotten, if they have no offers, then there's nothing for them to do. If they have one offer, they also have nothing to do. But if they have more than one offer, they reject all of them except for the best one. So every offer that they currently have except the best one, where the best is based on their own preferences. So to be clear, this also includes, so they may have had an offer from a previous round that they didn't reject, and maybe they got a better one now, they would reject that one from a previous round. So including pending offers from the previous round, if they exist, right? Okay. And basically this algorithm stops when every company has made an offer that wasn't rejected. Okay. And then when you stop, basically that company gets assigned to whatever intern hasn't rejected them at that point. Okay. It's a bit of a long kind of spiel, but I think it's a fairly simple algorithm. But any questions about how it works? So right, you can think in the first round, everyone makes their offers. You might have some candidates getting like 5 offers, some candidates getting no offers, right? But then, yeah, everyone rejects. Like if all the companies had the same preference list, for example, they're all making offers to the same person, and that person's just going to reject everything except the one they like the best, and so on. Okay, so I claim that this always finds a stable matching, and that it's also polynomial. This algorithm. Okay. So first, I want to. So it's not even clear, actually, at first that this always gives you a perfect matching. So that's something I'm going to do first. So yeah, so this algorithm always produces a perfect matching. So like we're assuming there's n interns and n companies, right? So okay. Well, okay, if not, so if not, then there's some, you could say there's some intern that's not matched to anyone, but you could also say there's some company. There's the same number of both. So let's think about the companies. So there must be a company C that is not matched, like not saturated. Meaning like all of its offers were rejected. Okay. this is kind of it's going to be a weird argument, to be honest. But it works. So how could this happen? I've got a company C. So it's gone through all of its candidates and made an offer to the best one, then the next best one, and all of them got rejected, right? But that means all of the interns got a job offer from C, right? Because it's gone through its whole list and everyone rejected them. So therefore, every intern got an offer from C at some point. But then, okay, that means every intern got at least one offer because it got one from C. So every intern got at least one offer because, in particular, they got an offer from C. But now if we think about how the algorithm worked, like if you're an intern and you got an offer at some point, you never rejected all of your offers. You always kept the best one. So at the end of this algorithm, if every intern got an offer, then every intern has kept their best offer. So every intern gets matched to somebody. But there's the same number of interns and companies, so that's a contradiction. So since every intern that received an offer must have kept their best offer. Every intern is saturated. But yeah, they're the same number of interns as there are companies. So since there are n interns and n companies, it must be a perfect matching. Does that logic track?
So the algorithm doesn't produce it matching implies that it produces perfect matching.
Yeah, exactly. Yeah. I feel like it is a weird kind of backwards, like backdoor way of getting this, but I mean, it seems like it works. Okay, so it is a perfect matching. Oh yeah.
Does it not just apply by the last statement?
I don't know, because yeah, what if there was a company? Oh, right, I see what you mean. Like I've kind of written it's a good point. Or, well, I guess, but actually, okay, maybe this stopping condition wasn't well defined because it's not even clear that that would ever happen, because maybe some company exhausts all of their list and never got accepted. So maybe I should say stop when every company has an offer that wasn't rejected or has run out of candidates. So, or a company runs out of interns to make offers to, because that could happen.
Yeah,
I mean,
you're just stepping in anything up to
yeah.
never end.
Well, also it's not, I haven't even explained, like it's not even clear if it's an infinite loop, because like if I've offered to the last person already, what's the next one on the list? There is no next. So maybe you go to the top, yeah. So yeah, that probably should have been a possible stopping condition. Of course, in this claim, we've proven that the second condition never happens. Truly, the first condition happens, but we don't know that at that point, right? That's a good point. Okay. Any other questions about that? Yeah, that's a better way to, I mean, this, yeah. Okay. So now I claim it's a stable matching. Okay, so let's do it by contradiction. Suppose not, and let I and C basically show that it's unstable. So maybe I'll just call it an unstable pair or something. So the intern I wasn't given the job C, but it prefers it. And C wasn't given the intern I, but they prefer that intern. Okay. But here's the thing. So C prefers intern I over the intern that they got, right? But think of how the algorithm works. They go through their list one by one, right? So at some point they gave I an offer, right? So since C prefers I over the intern they received, they made I an offer at some point. Okay. But the fact that they're not matched with I means that I must have rejected them, right? But there's only one reason to reject a company. It's because you already have a better offer. So at that point, I had a better offer, and that's why they rejected C. And actually, after that point, they may have rejected that one too, or something. But like the quality is just going to go up, right? The only reason they're rejecting anything is because they get a better offer. So at the point when they rejected C, it's because they were matched with a better company than C. And after that, they only get better and better. So when I rejected C, so it may have been immediately when they got the offer, or it could have come later. But at some point, I rejected C. It is because they had a better offer. Oh, but that means that whatever they ended up with at the end is better for them than C. So I prefers the company they're matched to over C. Okay, so that proves that's a, because yeah, they got a better offer at some point and it only got better after that, so. Okay, so it must be stable. Okay, so this algorithm shows that stable matchings always exist. And now I guess we should think about if this algorithm really is polynomial time. Okay, and well, I guess to do that we can just bound like how many rounds there could have been in this algorithm. Because, okay, each round, I think, can be implemented in polynomial time because you just, yeah. They make an offer to the best thing, like none of that takes a long time. Make an offer to the best thing on your list. Each intern reject everything except the top offer. Like all of these things are pretty easily polynomial time. It's just like the question is, could the number of rounds be like completely out of control, right? And it can't be. So, and the reason is really simple. So in every round, at least one company makes at least one offer. I mean, otherwise, we wouldn't be doing that round. And no company offers the job to the same intern twice. Okay. All right, just by how the algorithm works, it never goes back to someone it's been rejected by before, and so it never does it twice. So yeah, the number of rounds is then going to be at most the number of interns, or let's say number of companies, times number of interns, which is n squared. So because, yeah, the number of pairs company intern is at most this much. Every round, some company makes an offer to some intern, and it never gets repeated. So, and then each round is also polynomial, so the whole thing is polynomial time. Okay, so far we've focused on just matching in bipartite graphs pretty much. So now we're going to kind of think about more general graphs, which it's more complicated, but maybe one thing I will say, we're not going to prove this but it is a doable thing that so I'm going to kind of make a note that let's say, maximum, generally matching problems like including, for example, maximum weight matching in general graphs can be solved in polynomial time. Okay, so this is something known as it's a very famous algorithm called the Blossom algorithm. I'm not actually going to cover it in this class, but it's a good thing to be aware of. Actually, maybe it's like a good, in this course you have to do a project at some point. This could be like this is a bit beyond the course, but very relevant. So this is the type of thing that one might be able to do. But yeah, we're not going to actually give this algorithm, but we're going to do some things related to it. Okay, so let me kind of give a few definitions that we're going to need. So a component in a graph, probably a lot of you are familiar with what this means. It's like if this is my graph, these are the three components. It's like the connected sets of vertices, like the maximal connected sets of vertices. It's the stuff where in any component you can get from every vertex to another, but you can't get between different components, right? So a component in a graph is a set C in the vertex set, which is kind of maximally connected, let's say. Meaning that, for example, this set would be a component because it's connected. You can go from any vertex to any other vertex, but it's maximal with that property. If I added another vertex like this one, it would become disconnected. Right. So, okay, here's a definition which is, it's really unclear why this should matter, why this would be a natural definition, but it turns out to be very important in matching problems. So let O of G, so this is like a little, so this is not asymptotic notation, this is just the letter, anyway. Let's let O of G be the number of components of G with an odd number of vertices. So the O stands for odd. I guess for this graph, I guess O of G would be 2, because that one has 3 vertices, that one has 5, that one has 4, right? Okay. Okay, so this is what we're going to prove next. Something called the Tutte-Berge formula. Which just says for any graph G, so nu of G, which is the size of the biggest matching, is equal to 1/2 times the minimum over all subsets of the vertices of the quantity number of vertices of G minus the size of S, plus the size of S, minus the number of odd components of G take away S. Okay, so this notation just means the graph you get by deleting S, the vertices of S. Okay, and when you delete a vertex, it also deletes all the edges touching that vertex. it shouldn't in any way be obvious why this is why this formula makes any sense, but is it clear what the formula means or what it says? Okay, so like I said, I'm not going to give you the polynomial time algorithm for matching problems, but this formula by itself should be kind of good evidence to you that matching problems are probably solvable in polynomial time. At least finding the biggest matching. Maybe not weighted matching, but finding the largest matching. Because, like, what is this saying? This is the max of something, which is equal to the min of something else. This type of a theorem is going to come up over and over and over in this course. Like, for example, duality in linear programming. The max of the primal equals the minimum of the dual. So in some sense, yeah, this is a maximization problem, finding the biggest matching. This is kind of a dual problem, finding the minimum over all sets of vertices of this, whatever this weird quantity is. And yeah, when you have a problem where of this form, like it's often going to be a polynomial time solvable problem because, for example, if I gave you a graph, an integer k, and I gave you this decision problem, does it have a matching of size k? That would be an NP, because you just give them the matching and that's the certificate. Right? So if the answer is yes, there is a matching of size k, the matching of size k would be the certificate. If the answer is no, there isn't a matching of size k, this is the certificate. Find a set S where this quantity is less than k. And then that shows that there isn't a matching of size k. So this means that problem's in NP and co-NP. Yeah?
Because there's 2n different
Yeah.
subsets of vertices, it seems like even just calculating that should be exponential.
Yeah, so I'm definitely not saying that this theorem gives you a polynomial time algorithm. It doesn't. Because to compute this, you're right. I mean, also to compute this, you'd maybe look at all this. I don't know what you would do, but also to compute this, yeah, 2 to the n steps, right? So I'm not saying this gives you a polynomial time algorithm, but it tells you that this related decision problem is in NP and co-NP. That's all I'm saying. So if I had the problem where the input, so yeah, so this doesn't give you a polynomial time algorithm. You have to do this Blossom algorithm to get that. But if I have this problem where the input is a graph G and an integer k, and then the question is, does G have a matching of size k? If I have a yes instance, then a certificate is just give me a matching and you can check it has size k. If it's a no instance, the certificate to show that it's no would be to find an S that has, where this number is less, this right-hand side is less than k. Now I'm not saying that S is easy to find, but it's easy to check. If someone gives it to you, you can just compute this. So that tells you that this problem is in NP and co-NP. Belief that maybe, like it's not known, right? But this is a thing that, so is maybe believed that maybe P is NP intersect co-NP, which would mean that this problem, by being in here, if this is true, this would be polynomial time solvable, okay? It is polynomial time solvable, but not in a way that we're going to do in this course. But anyway, I guess what I'm trying to say is this formula gives you evidence. Like if this is true, then it would be polynomial time solvable.
So everything we found that's in NP and co-NP has been polytime at some point?
Yeah.
Or there has been a polytime for some point?
Yeah, yeah. And probably, I think everything we'll see in this course, like sometimes we'll prove a theorem that proves this, and then maybe we'll give an algorithm separately. or maybe we'll just prove this and not give the algorithm, but that it's suggesting to you that probably it's polynomial time solvable, and all of the ones we'll see in the course will be polynomial time solvable, yeah. But a big theme of this course is having a maximization problem that can also be solved by a minimization problem, which basically gives you this, and then it's probably polynomial time solvable. Okay, so yeah, that's how you should interpret this, that this is a good sign for matching problems. Any other questions? Okay. Yeah, I'm glad we went through this because I think I sort of tried to convey this earlier, but I don't think we didn't have enough examples at that point, so it doesn't really go through. But we're going to see more and more of this. The max of something equals the min of something, and that's like a very good sign that it's polynomial. Okay. So let's prove the upper bound first. Yeah. So I want to prove kind of this direction. Nu of g is at most this quantity. So let M be a matching. And let S be a set of vertices. Okay. So yeah, so I'm going to prove that the size of M is at most like this quantity. And then the size of M will be at most the min, and then the max matching will be at most the min. So I'm showing every matching and every set of vertices satisfies this inequality. Okay. So there's kind of a picture that I've got in mind where I've got like S in the middle, and then I've got components. So when I delete S, you get some components of the graph, right? I mean, it might just be one component for all I know, but you have some number of components. Each component, so let's say C of G take away S contains at most the number of vertices in C over 2 rounded down edges of the matching. Right, because because every matching edge hits 2 things. So if it's an even component, maybe it might hit the vertices, like it might cover them perfectly. If it's odd, then there's always going to be somebody left out, right? But so yeah, let's say the edges I'm drawing are like in M maybe. So each component of this thing contains at most that many edges. Okay. And then there might be some edges of M that are like in S, and maybe there are some edges of M that like kind of go from S to these components or something, right? Who knows? But one thing I can say is that the number of edges of M with at least one endpoint in S is at most the size of S. Okay, because like they can't hit the same vertex twice, right? any edge like this covers one, like if it has exactly one endpoint in S, then it covers one vertex of S. If it has two, it actually covers two of them. And you can't cover the same thing twice because it's a matching. So everything that has at least one endpoint in S is covering something in S, so there can't be more than S of them, size of S, right? Okay, but the thing is every edge of S or of M has one of those two properties. Either it's contained in a component or it has an endpoint in S. Maybe two, but at least one endpoint in S. So therefore, so the number of edges in M, well, let's take the ones that touch S. So then for the vertices that are not in S, we kind of get a, like for each component, yeah, that's not of G minus S, we get, yeah, basically half, except every time it's odd, it rounds down. So we should subtract 1/2 times the number of odd components. And actually, this ends up being if you do the math, because this is like size of S minus like half of the size of S, so you get half of the size of it, but there's a half here. That's all the vertices with a half, and then you've got like that with a half. I think it works out. Okay. So that proves the upper bound. So yeah, then, so if every matching in every set S satisfies this, then the biggest matching and the minimum S will satisfy this inequality as well. Does that part make sense? Okay. So now we show that there exists a set S such that nu of G is at least 1/2 size of the vertices plus size of S minus odd components of G minus S. Okay. So we're going to do this by induction. On the number of vertices of G. Okay. And I don't know, the base case, one vertex, I don't know, check. Yeah, 0 equals 0, I think. So that's not a, let's not worry about one vertex. We can also say we don't need to worry about the case when G is disconnected. So you might take a bit of thinking, or maybe not. So we can assume G is connected. Otherwise, just like apply the theorem to every component separately. They're all smaller than G. Use induction, and I think it should check out. So otherwise, apply the theorem to each component. Okay. This is gonna. Okay, we're gonna break the proof into two cases. And frankly, I have no intuition about why you would pick these two cases. I mean, maybe you can build up some intuition, but yeah, it's going to seem kind of clever. But yeah, so case one is that there exists a vertex V such that every matching of size, so of the maximum size, saturates V. So if you want to get a big matching, you kind of can't avoid hitting the vertex V. Okay. I don't know, any guess like what we should do with this vertex? I don't know. I have no intuition either, but I just know we're doing induction, so yeah.
Doesn't perfect matching have max size and necessarily touch?
Yeah, if in the case where you have a perfect matching, then every vertex would satisfy this criteria. So you could pick V to be anything.
Not necessarily.
Nah, so this has to work for every graph of every possible matching size. So the biggest matching, I mean, it could be the graph could be that, right? And then this is my V, because the biggest matching is size 1, and it always hits that one. So I don't know. I mean, we're doing induction. Let's just delete V and see what happens. I mean, so we have this special vertex. Let's just say, okay. Well, so one thing I can say is that if I take the biggest matching after deleting V, it's gone down because V is in every biggest matching. So when I delete V, we don't have those matchings anymore. So it's going to be lower by 1. Okay. And now we can apply induction. So by induction, there's a set T in the vertex set of G, take away V, such that so like I'm applying induction to this graph. The matching number of this graph is just this number, right? So I'm just going to write nu of G minus 1, which is equal to that. And that should equal 1/2 times the number of vertices in this graph, which is the same as my original graph minus 1, plus the size of T, minus the number of odd components in the graph G, take away V, and also take away T. Okay. In this case, actually, we're in good shape. So I'm just going to let S be the graph T, or sorry, S be the set T, and then add in V. we need to check that the formula works. I guess maybe this case maybe is natural because this is really saying, is there a vertex where the matching decreases? If that exists, then you apply induction and you take that vertex and you put it into the set S at the end. So maybe there is some kind of natural thing here. So I claim that this has the right properties. So yeah, I mean, if you kind of solve it, if you add a 1 to the other side, so add 1 to both sides of this equation, that there's a half here, so that puts like a 2 inside of these brackets. One of them cancels that -1. One of them adds 1 to that to make it the size of S, right? Because the size of S is 1 bigger than T. And then this thing, you don't have to worry about it because this is actually just G minus S. Right? Because it's G take away V take away T. It's the same as G minus S. So yeah, so this works. So the formula holds just because, yeah. Take this formula, add 1 to both sides, do some algebra, and it is the right thing. Okay, so case 2 is, I guess, no such V exists. Okay, so definitely, actually this connects to this question about matchings earlier. Like when there's a perfect matching, every vertex would fit this criteria. So there's definitely no perfect matching because, yeah, then every vertex would be one of those. So, so there's no perfect matching. So we'll just say PM for perfect matching. So therefore, nu of G is certainly at most the number of vertices minus 1 over 2. Because if it was equal to V of G over 2, it would be a perfect matching. I'm going to claim that nu of G is, it's got to be equal to that quantity. So that's what we're going to prove. And somehow this is going to be useful. Okay. Actually, maybe we can say why would this be good? Because then we just let S be the empty set, and we get, nu of G is the number of vertices of G minus 1 over 2. Okay, but then this other quantity, like 1/2 V of G plus size of S minus odd components of G minus S would just be equal to if S is the empty set, that's 0. That's got to be 1 because in order for that to be equal, V of G has to be odd. Like you cannot, I mean, the numerator has to be even. So this would imply, and so if S is the empty set, yeah, both sides end up being equal. Okay. So this is why we prove this claim. Is that clear? Just have to check the formula, basically. Okay. So suppose not. So suppose the matching numbers at most this, where I've got like a 2 instead of a 1. So let M be a biggest matching, largest, whatever. So there's got to be 2 vertices left out, at least 2. So, so let U and V be unsaturated vertices. Okay. And, right, because there has to be at least 2 of them. And moreover, we're going to choose these in a very kind of extreme way. So I'm going to choose M, U, and V so that the distance in the graph from U to V is minimum. Okay. So among all the possible largest matchings and all the possible unsaturated vertices, we're going to get these ones as close as possible. Does that make sense? It's not clear where we're going, but let's just go there and see what happens. Here's one thing I can say. U and V are not adjacent. If they were, you just add that edge to the matching and get a bigger matching. So UV is not an edge because M is maximal. Because, yeah, M. And otherwise, I'd just throw that edge into M. So if you take a shortest path from U to V, there's some vertex in the middle, at least one, maybe lots. But so we can let W be a vertex on a shortest path from U to V. Okay. Now what I'm going to do is use the fact that we're in case 2. By case 2, I know I can find a maximum matching that doesn't saturate W because we're not in case 1. So let M prime be a maximum matching that does not saturate W. Because, yeah, if that does not exist, we'd be in case 1. This is going to seem like a big rabbit hole. I'm just going to keep doing stuff. And then it's not going to be clear why this is the right thing to do. But, yeah, and we're going to do this such that the intersection between M and M prime is as large as possible. Okay. So among all such M primes, pick the one with the biggest intersection with M. Okay. So note that the distance from U to W is less than the distance from U to V, right? Because W is somewhere on the shortest path from U to V. And so therefore, by the way I chose M and U and V, And the fact that M prime doesn't saturate W, it must saturate U. Because otherwise, I could choose U, W, and M prime to be my U, V, and W. Or sorry, U, V, and M. Okay, so M prime saturates U by our choice of U, V, and M. Because if it didn't, I've now found closer vertices that get missed by some biggest matching. Okay, and similarly, it saturates V. Is that clear? Well, so we know it saturates U, it saturates V, it doesn't saturate W, but like the maximum matching, again, it's less than, it's at most this. So there's some other vertex that doesn't get saturated. So there exists a Z, which is not U, V, or W, that is not saturated by M prime. Oh, sorry, no, I need more than this. Sorry. There's some Z that is saturated by M, but not by M prime. So this, I also need the fact that, that these things have the same size. To get that. Okay. It's not really coming to me completely why this is the case, that it could be saturated by M but not M prime, but the fact that these matchings have the same size somehow gives that to you. So maybe let's take this as a given for a second, because I don't have a lot of time here. So since it's saturated by M, we can let Y, Z be the edge of M containing Z. Okay. So I claim that Y is saturated by M prime. This is like a wild rabbit hole that we're going into, but so Y is saturated by M prime. Why? Because I know Z isn't. So if Y also isn't, I would just add that edge to M prime. We could, so otherwise we could add YZ to M prime and get a bigger matching. Okay. So now I'm going to define yet another variable. So now let XY be the edge of M prime that contains Y. Because I've said that Y is saturated by M prime, so there's some edge, XY, of M prime that contains Y. Okay. So now define M double prime to be, I'm going to take the matching M prime. I'm going to throw away the edge xy, which is in there, right? We just said it is. And instead, I'm going to put in the edge yz. Okay. This is a matching because after I throw away xy, like z was not saturated by M prime. So after I throw away xy, they're both not saturated, so I could add that edge in. So it's still a matching. It still has, so M double prime is a matching of the same size as M prime. Yeah, sorry. Has the same size as M prime, but if I look at how much it intersects with M, it's supposed to be more than the amount that M prime contains of M, I guess because the edge yz is in M and that one wasn't. I mean, they couldn't both be in M because they both have y in them. This one's in M, this one isn't. I've swapped. And this has all the same properties that M prime should have had. So it's like, it's the same size. It doesn't saturate W. The reason is because W is not the same as Y, because we, at some point in this long story, we said that W and Z are not adjacent, I think. Wherever that was. And yeah, so this contradicts the choice of M prime. Okay. And so that should complete the proof.